In this video, we're going to begin to look at waves and vibrations, and we're going to start with periodic motion and describing what periodic motion is. And some essential questions that we're going to answer in this video are: what is simple harmonic motion? How much energy is stored in a spring? And what affects a pendulum's period? So some review vocabulary: we're going to use the gravitational field, and we're going to use baby G here, 9.8 meters per second squared. And some new vocabulary is going to be periodic motion, a period, amplitude, simple harmonic motion, Hooke's law, simple pendulum, and resonance. If we consider a mass on a spring, and we have a spring that's hanging vertically, and we hang a mass on it, and we pull the mass down so that it oscillates back and forth. This is an oscillatory motion, and that's movement of an object that goes back and forth between two opposing positions. So you can imagine the spring going up and then down and up and down, and this repeated motion we call oscillatory motion. And any motion that repeats in a regular cycle like this is an example of periodic motion. It's called periodic because it repeats over a period of time, and in a given period it goes through an entire cycle of its motion. Some examples of this would be a mass bobbing down on a spring, or say a pendulum swinging back and forth, a vibrating guitar string, or a tree swaying in the wind, or maybe you've seen bridges that sway, or signs that move back and forth in the wind. And in each of these examples, the object has one position at which the net force on it is zero, and at that position, the object is in equilibrium. That position is called the equilibrium point of the simple harmonic motion. Anytime we have an object that is pulled away from its equilibrium position in this simple harmonic motion, the net force on the system becomes non-zero and pulls the object back toward the equilibrium. In any system in which the force acting to restore on an object to its equilibrium position is directed proportionally to the displacement of the object shows simple harmonic motion. So as pictured to the right here, if we exert a force on this mass and move it away from the equilibrium position, and we continue to move it away from the equilibrium position, we're exerting a force, and then this spring is going to exert a force back toward the equilibrium position. And if we release it, this will oscillate back and forth and back and forth, and this will show us this simple harmonic motion. Now we can use two different quantities to describe simple harmonic motion, and that is the period and the amplitude of the motion. The period is, and we use T to denote the period, a capital T. This is the time that is needed for an object to repeat one complete cycle of its motion. So we're talking about going from one end to the other end and then back to the original first spot, and that is one full cycle. So going from one spot, going through the cycle, and back to its original spot, that is a full cycle of the simple harmonic motion. The time it takes to complete that, we call the period. The amplitude of the motion is the maximum distance the object moves from the equilibrium position. So this distance right here from the equilibrium position gives us the amplitude. So we notice that the spring in step 2 here has a smaller amplitude than that one in step 3. When we're dealing with springs, we have to bring in this law called Hooke's law. And Hooke's law basically states that when a force is applied to stretch a spring, such as hanging it on its end, there is a direct linear relationship between the exerted force and the displacement. And so with a direct linear relationship, that means we can graph these two, and we can see that the slope of the graph is equal to this thing we call the spring constant. All right, and the spring constant talks about the stiffness of the spring, how easy or how hard it is to stretch or compress the spring. The area under the curve here, now this is when we plot the magnitude of the applied force and the distance that it's stretched. The area under the curve here equals the elastic potential energy that is stored in the spring as a result of that work. And so we can look at Hooke's law and use that graph and use the slope to be the spring constant we call K, and we can come up with a formula saying that the force that the spring exerts on an object is equal to the negative of K, which is the spring constant, times X, the distance that we stretch it from its equilibrium point. And like I said, K is the spring constant, which that depends on the spring itself, the stiffness of the spring, how many coils it has, all those things. It's typically going to be something that's given, or maybe we solve for that spring constant. And X is the distance that the spring is stretched from its equilibrium position. The potential energy that is stored in the spring, like we said, is the area under the curve, and that's equal to 1/2 kx squared. And so the potential energy, we increase as x increases, but then we decrease as x decreases. So as we get closer to the equilibrium point, our stored potential energy is now gone and it's converted into kinetic energy. So if we look at this graph that graphs the displacement of a spring that's oscillating back and forth as a function of time, we can see that at these different points that are on the graph, we have different values of our potential energy due to the spring and our kinetic energy due to the motion of the object. So at the first point, we have all potential energy, and then the second point we have a combination of potential and kinetic, then we convert to all kinetic at the third point, then we're back to all potential, then we have that shared potential and kinetic, and then finally we're up here at all potential energy. And so we oscillate back and forth between the potential and then the combination of potential and kinetic to all potential, and then back to the combination until we get back to just all potential energy. And so this is just oscillating back and forth and back and forth, and we're converting potential energy to kinetic and kinetic back to potential energy. Let's look at an example problem here. And we have a 560 Newton cyclist that sits on a bicycle seat and compresses the two springs that support it. The spring's constant equals 2.2 times 10 to the fourth newtons per meter for each spring. How much is each spring compressed, and by how much does the compression increase each spring's elastic potential energy? So let's take a look at the problem here, and we have two springs that we are compressing a distance x due to the force of gravity. The key to this is that the force of gravity is going to be split in half so that each spring is only supporting 280 newtons instead of the full 560. The 560 split between the two springs. And so we have the force that the spring is exerting and the spring constant. We want to know how far is this compressed, so what is x? Well, we can solve for the unknown using Hooke's law and using that x is equal to F over k, and we can solve and get 1.3 times 10 to the negative second meters. And if we want to find the potential energy, well, potential energy is going to be 1/2 kx squared. We have all of this information now, and we can see that there is a potential energy of 1.9 joules stored in the two springs. And so we can double check, does this make sense? Well, yeah, we're only compressing it a very small distance, so we're talking about just a centimeter, centimeter and a half, and the energy, not a whole lot of energy is stored in this, just about 2 joules. A pendulum is another example of simple harmonic motion in that it has this periodic motion that repeats back and forth. The difference here, our conservative force is not the elastic force of a spring, but the force of gravity. And so we consider a simple pendulum to consist of a massive object, and we call that the bob of the pendulum, and it's suspended by some type of string or a light rod of length L. Now, typically we say this string or rod is massless, or the mass is negligible compared to the mass of the bob. And the period at which this swings back and forth through its motion is dependent upon the length of the pendulum and the gravitational field, but not the bob's mass. And this is very important because it's kind of counterintuitive in that you would think that the heavier the object that you put on the end, that would affect how quickly it swings back and forth. But in fact, it doesn't affect it. What affects it is the length of the pendulum arm and the gravitational field. So as long as we're on Earth, that gravitational field is going to remain constant. And so we have an equation to find the period of any pendulum by 2 pi times the square root of the length divided by the gravitational constant, or in our case, 9.8 meters per second squared. So looking at an example here, we want to know what is the period of a simple pendulum that has a length of 0.25 meters. Well, we can look at the situation here. We have a pendulum bob. The length is 0.25 meters. We want to find the period that's our unknown. So let's look at our equation. It's already solved for the unknown, so we just have to plug in our values, and we get 1 second. So if we want a pendulum that has a period of 1 second, it needs to be 25 centimeters. Lastly, we are going to talk about the idea of resonance. And resonance occurs when small forces are applied at regular intervals to a vibrating or oscillating object, and the amplitude of the vibration increases. The time interval between applications of the force is equal to the period of oscillation, and that's important. If we don't have that force being applied at even period intervals, then we're not going to get this resonance frequency. And an example of resonance here would be if your car's ever been stuck in the snow and you rock it back and forth and you push it at even intervals and you push when it's at its maximum, or just pushing someone on a swing. That's an idea of resonance, in that the amplitude is increasing because you're giving them a force at the same time interval every time. Also, jumping on a trampoline or a diving board, you're getting that same force at the same time interval to increase your amplitude. Hopefully in this video you were able to answer these 3 essential questions and have a general idea of these vocabulary terms.